Okay, 5 to go. I'm going to assume that if you have clicked play on this video and it didn't just pop up in your YouTube queue, it is because you have already watched this video, and you've already seen this, and you've already seen this, and you wrote this down in a notebook, and it was super important to you, and you watched me do this example, and you watched me do these examples, and you're like, maybe I can almost do this, and you saw those, and you're like, gosh, I hope trig never comes back, but whatever, and you tried the OYOs, and you're like, well, maybe I'll stop in an office hour, and then you hit the worksheet that attaches itself to this lesson, and you said, wow, I'm going to work through as many of these questions as I can on my own, then I'm going to click on the video and see what the answers are. So if that's the case, you're in great shape, and I'm glad to help. The questions start out basic, and then they get a little bit more complex, and then tomorrow we get even more bizarre, but that's tomorrow. So for now, what's the big deal? The big deal is that thing in parentheses, that thing has a derivative which happens to be hiding out right there. And whenever that's the case, I think U substitution. Whenever there's a part of the integral whose derivative is hanging out right nearby, I think this is a U substitution. So we let U be the thing whose derivative is hiding nearby, and then we make a complete substitution. We get rid of everything that smells like our X and replace it with something that smells like U, and that's how this works. So the 3x squared dx, that becomes du. The x cubed plus 2, that becomes u. There is no x anywhere over here anymore. We have replaced everything that looks like x. Even these. When x is 0, what's u? When x is 1, what's u? And now, here's the big point. We recognize that the answer to this is the same as the answer to this. So we forget that this ever existed. It's gone. And we do this problem instead because this problem has the same answer. Well, why do we do that? Because this is easy to find an antiderivative of. The antiderivative is just 1/3 u cubed. This is fundamental theorem of calculus part 2. We find an antiderivative, sub, and subtract. Sub, and subtract. And that happens to be 19/3. This integral has the same value that one does, so we do this one because it's easier. Same sort of thing's going to happen over here. This is in parentheses, which means it makes a really good u. But what's du? Well, that's the derivative of 2x minus pi. That's the derivative of 2x minus pi. So du over dx is equal to 2. So du is equal to 2 dx. There's a dx. There's no 2. Well, sure there is. You're like, wait a minute. You can't just put a 2 there. I know. We compensate. So what does this become? Well, the 2 dx gets replaced by du. And the cosine of thing in parentheses is just u, gets replaced by cosine u. And then we check out what happens to these when x is 0. What's u? When x is pi over 4, what's u? And now we recognize this integral has the same answer that this one does. So we do this one because it's easier. Fundamental theorem part 2 says you find some antiderivative, sub, and subtract. sub, sub, and subtract. And that turns out to be -1/2. How can an integral be negative? Well, if more area is below the x-axis than is above the x-axis, the integral can be negative. Same sort of thing happens here. There's a part of our integral whose derivative is hanging out right here. So we let u be x squared plus 1. I don't want to be x squared plus 1. Well, too bad. You are. The derivative of x squared is 2x, so du dx is 2x, so du is 2x dx, and we go replacing things. The 2x dx, that's du, which means there's no 2x anymore, and x squared plus 1, that's u. When x is 1, what's u? When x is 4, what's u? And now we recognize that this integral has the same answer that this one does, so we do this integral because it's easier. We take an antiderivative, sub, sub, and subtract. Sub, sub, and subtract. Now, it would be sufficient for you to leave it like this. In the back of the book, they're going to write it like this. And I'm going to give you a moment just to refresh yourself on why this would turn into that. Okay. I have asked this question on a final exam before. I have asked this as a short answer where I give you the answer. So you can't just say, well, I put it in my calculator and I got this answer. I'm looking for a U substitution here. This is another question where the thing in parentheses or under a radical or raised to a power or in a denominator happens to have a derivative that's basically staring at you somewhere else in the integral. Now, warning, there's no 2. Right? We need a 2. There's no 2. Oh, look at that. There's a 2. You can't put a 2 there. That's just, okay. I got that. That's okay. So then what is this? Well, the 1/2 comes along. The 2x dx gets replaced by du, which means there's no 2x up here anymore. And then you got this thing in your denominator. From where to where? When x is 0, what's u? When x is 7, what's u? This integral has the same value that this integral does, so we do this integral because it's easier. Why is it easier? Because this is u to the -1/2. And if u to the -1/2 is the thing we're integrating, then we know how to do that. Its antiderivative raises the power by 1 and then divides by that power. So raise the power by 1, that's u to the 1/2. Divide by 1/2, that's times 2, knocks that out. Great. Great. So we sub, sub, and subtract, and we got it. Fundamental theorem of calculus gives us everything we need there. I asked this question on a final exam in years past, and you would be amazed how many students were unaware that this thing in parentheses made a really good u. Because if that's u, then du is derivative of that dx. So now this part is this part, gets replaced by du. X squared gets replaced by u. Integrating from where to where? Well, When x is 0, what's u? Where x is 1, what's u? And then we realize that this integral has the same value that this integral does, so we do this one because it's easier. Well, wait a minute. Why is it easier? Well, because we already have this piece of information. And it's a curious thing that we talked about in a previous lesson. This actual variable here, this is what we call a dummy variable. It literally does not matter. You can do f of x dx, you can do f of t dt, you can do f of p dp, you can do f of smiley face d smiley face, and you can do f of u du. And all of those are the same thing. So this is this is this. And we're done. We're done. Two more before we're done. So yes, I said we're done, and then two more before we're done. Two more before the video ends. Looking for this thing in parentheses. That's probably a really good u. The derivative of 5 minus x is -1. And so, wait a minute. We can't replace this because we don't have all of this. So we multiply on both sides by a -1. And so this is -1 times the integral of f of u du. From where to where? When x is 1, what's u? When x is 4, what's u? And you're like, man, this is so close to this. I'd love to have that happen. Oh, wait a minute. If you reverse the limits of integration, reversing the limits of integration is just multiplying by a -1. So then you have negative. So this has the same value that this does, and this is that. Done. Done. Okay, last one. This is a curious way to write things. So I'm going to do the u substitution here. I'm going to let u be x minus c. The derivative of x is 1. And so dx can be replaced by du. F of x minus c, that's just f of u. And it's an integral from when x is 1, what's u? When x is 2, what's u? Oh, what are we interested in? We're interested in this, which looks an awful lot like this. And this integral has the same value that this integral does. Done. So what is super important for you to remember? Things in parentheses make really good use. Things in radicals make really good use. Things raised to powers make really good use. And so I hope you make good use of what you have learned in this video. Ha! Gosh, can you tell it's the end of the semester? Okay, see you next time.